Here we go. So in the last class, or a couple classes, we are now bridging the gap from approximate to exact accumulation. Here's just an image of that sand example, the sand unloading with the weight, right? So what was our approximate net accumulation function? First of all, which one of those functions is the approximate net accumulation? R sub f, A sub f, or A? Which one's approximate net accumulation of those four? My front row knows. Yes, ma'am. In the back, tell me. Just A. Just A, right? That's this piecewise linear function that we were able to write in one rule, which was this rule, okay? That's our approximate net accumulation function. And so from that, we said we're going to have our exact net accumulation, which is our A sub f. And could you write down what A sub, how do we represent the rule for A sub f? Could you write that down if I asked you to do that? What is A sub f? What is A sub f? Jacob?
It's going to be the integral going from A to x.
Integral from A to x?
R f of x times t times dt.
Good. Nailed it. Okay. So this is what we said is our exact net accumulation function. And we'll talk about that more in a second. Okay? And so how do we think about this meaningfully? A sub f of x is the accumulation of changes in f due to its changing rate, r sub f of t, at every moment t from A to x. So t, remember that t starts at A and increases up to x so that we can actually have that exact rate function going to work for us as x changes from A to the final value of x. Okay, so this is the accumulation of changes in f due to the changing rate r sub f at every moment t, starting from A and ending to x. Okay, that's the meaningful way to read that. All right, and so then we could talk about exact total accumulation. So suppose the scale already had p hundreds of sand on it before we started unloading with the truck. Then the function f, which is not shown down here, the function f would be the exact total accumulation, and how would it be different than the exact net accumulation? Yeah?
You would add f of A to the...
Okay, but so the scale has p hundreds pounds of scale, has sand on it. So what would it be then? We can do better than f of A, right?
Yeah, then you would just do p plus A sub f.
Right, so if this is the accumulation of changes in the weight of sand, and we want the total accumulation of sand on the scale, then it'd be the accumulated amount starting at A plus the original amount P that we had to start with, right? So if there was P hundreds of pounds of sand on it, then our function for total exact accumulation would be P plus that integral, giving us the amount of change, right? So the initial amount plus how much it changed up till time equals x. All right, so any questions on that? So we're gonna talk lots more about integral today. We really got to understand what this integral is about. Questions on that kind of overview? Exact net accumulation, exact total accumulation. Are we good? All right, so whenever you see an expression like this, an integral function, like the integral from A to x, r sub f of t dt, this notation is a reminder of, what is it a reminder of? It's a reminder of this, right? It's representing this, but for a certain case of this. What certain case of the A function is the A sub f function? What certain case of it? It's not always that, so that integral function is not always equal to this, but only when what? I know Kyle knows. Aiden.
It's an infinitely small delta.
Right. So and not even so infinitely small certainly works, but what we've been saying is just small enough so that we can't distinguish, right? So it's just we have a small enough value of delta x so that the values of A are indistinguishable from the exact accumulation. We can't tell the difference. We can't tell the difference. Okay? So when you see the integral function, you think of this one with a really, really super small delta x, so that this is virtually giving us exact accumulation, and we represent it that way. Okay? And in that case, all right, so then the partial interval here, if our delta x is that small, then the partial interval has no contribution, really virtually no contribution to the accumulation, and so we don't need it, okay? When delta x is super small like that, we can just disregard, because that's not contributing to the accumulation at all, because it's even an interval smaller than delta x, which we said was super small anyway. You see? All right, so let's talk about comparing these two. And so how are these the same? For each, so you're going to work through these. You're going to talk with the person next to you. For each item, 1 through 6, you're going to go to both expressions. You're going to see, how is that item? Say number 1. How is number 1? We know how fast something is changing. How is that seen? Where is that represented in the first one? And where is it represented in this form? Then go on to number 2. We want to know how much of it we have. Where is that represented symbolically in the first one? And then where is number 2 represented symbolically in the second? You go through each 1 through 6 and talk those through. So both expressions entail all 6 of these items about this journey. We know how fast something's changing. We want to know how much of it we have. So take about 2 or 3 minutes. Talk through items 1 through 6. Go. So talk. You guys just to be talking. You're supposed to be talking. Did you already talk to all 6 of them? Okay. Yeah.
Is it delta x or dt?
What?
Is it delta x and dt?
Okay. Just give me. It's a change. It's a change. M dx.
Oh.
M rate times the change in x.
Okay. That was that question. Change in independent or dependent?
But we're not summing up changes in the independent.
Right. I know.
Yeah. So we're summing. Yeah. And it says delta y's. Eugene. It says delta y. Okay, so that okay. Where do we see in there? In each of those, we know how fast something is changing. So that's what we start with. We know how fast it's changing. Where do we see that in the first one? The R sub f function, the exact rate of change. Where do we see it in this one? The R function, right? So we know how fast something is changing. That's what we start with. The rate function. We see it in both of these expressions. We want to know how much of it we have. What's that?
The a sub f function, the a function.
Yeah, so this is the result, is we're making these functions that tell us how much we have. So that's the accumulation, right? We know how much of it we have at every moment, right? We know how much we have at every moment. So that is literally the functions that we have built out of the rate function, right? Okay? Which is found by summing up. Where do we see summing up something in the first one? Over here. Quiet corner, right here. Yeah, tell me.
So the first one is the integral and then the second one is the summation.
Right, so exactly. Integral is German S for sum. Sigma is Greek for sum, for S. Okay? So found by, we're summing up many, what are we summing up? We're summing up bits of change, bits of accumulation. So where do we see that in the first one? This is like maybe the most important one, number 4. How do we see a little bit of accumulation in the first one? Okay, in the back on this side. Okay, black shirt, headphones. What's your name? Jacob, tell me. In that first integral expression, where do we see a bit of change, a little bit of accumulation? What's that? D of t. That's where we see a little bit of accumulation. Agree with that? Behind him in the red shirt. Okay, this is the most important question. Yeah. Right. Changes in y we found it through constant rate of change as rate times change in independent. That's what we worked on for so hard, right? So a change in your y, a change in your accumulation is found by taking the constant rate of change times a change in your independent. Okay? That's how we get a bit of change. And so in the second one, we see it as r of that whole thing, right? This don't let this confuse you. All this is just, that's just all the argument into the r function. So this whole thing that's r, and then times a change in x. Constant rate of change says that a change in y is a constant rate times a change in x. This is the core idea of integral. Constant rate of change. And there's, you see it right there in that green bubble. M dx. If that wasn't clear before, let it be clear now. Constant rate of change is the core principle of integral. M dx. Here we go. Starting value of x is a. You were all thinking that, right? So starting value of x, so we see that there. The integral from a to x, and then we see the a and the floor function there, to the current value of x. Right? And so the current value of x, how does that relate to each of these functions? How does the current value of x relate to each of these functions? What is it relative to each of these functions? Robert?
It's basically where the function is told to end.
Right, yeah. So it's where we're gonna. It's currently where we have accumulated 2. Currently where we've accumulated 2, but then that x increases, so we get the whole function, right? So yeah, x is the right side of where we currently have accumulated 2, and what is it? What is it relative to the functions in terms of variable? Which variable is it? All functions are about 2 quantities, right? Variables representing 2 quantities. Which one is it? What's that? Independent. The independent, right? It's the independent variable. It's our x-axis. We put this on the x-axis of our graphs. So the independent variable into these 2 functions is where we've accumulated to. How much the ending value of x to which we've accumulated at any given moment, right? And so that we can let the moments increase, right? So that's the answer number 7. Is that x is the independent variable of these functions, and it's how far we accumulate to. It's the right side of all the current accumulation. All right? And then what's the output of each of these functions, right? So what is the dependent variable of each of these functions? So we know where we stop accumulating to the value of x, and so then what does the function give us? What's the dependent variable? I know that Kyle knows. How about right here in the black shirt and the glasses? Yeah. what is the dependent variable of these functions? When we progress up to the current value of x, what do we get? All right, we get the net accumulation, right? We get the amount of change since A. We get the amount of change in y, or whatever quantity we're talking about, since we started at little a. Okay? Super important discussion. Anybody have questions? So, when you see this, you think of this with a super small delta x, right? When you see this, you think of this, which we worked so hard on, right? We worked for a whole week on to develop that, with a super small delta x. Okay, so let's practice a little bit here. I've got some expressions. We're going to interpret these expressions. All right, so the first thing we're going to determine if it represents a valid accumulation. Remember, there was a problem. If we don't get those variables right, we run into a problem. So you're going to look for that first. If there's a problem, the problem we talked about last time, we can kind of stop the activity and move on to the next one. All right? Then letter B, we're going to identify all parts of the expression by their meanings. So we're going to relate all the parts to what we know integral means now. Okay? We're going to introduce function notation and rewrite it as a definition of a function or a particular value of a function dependent variable. So we'll do an example of that and then describe the meaning of a function as a whole. So let's look at this first one together. So first of all, does this validly do what we intend it to do?
Yes.
Does it get some amount of accumulation starting at 4 up to x according to this? And what is g? How do we see g? What is g? Good. So even though we're not using the same notation that we've used all along, so if you see the g of t, we just know that that's an exact rate of change function, right? So g of t is exact rate of change. And are we going to accumulate according to g, starting at 4 and ending at x? Yes, because we picked a different value t that will vary through all the moments from 4 to x. Where does the problem occur? Where does the problem occur? Remember from last time. If what?
If either the x in the situation of the t or if it was a function g of x.
Yeah, if these match, then we have a problem. We need a new dummy variable so that variable can vary from 4 to the final value of x. Okay? So we need something different here and here. When these match, then it's computing something valid, but not what we intended to compute. Okay? So we could write this then as a function. And maybe it's a sub, we're going to make something up, right? Because g is the rate of change function. So maybe it's, I'm just making this up, a sub z. Okay? And would it be of t or of x? Right, because remember our independent variable into this is how far we're accumulating to, right? So the right side of the interval for the current amount of accumulation. Okay, so we identified the exact rate function. Can you identify what all that is representing? What is all that representing? Tell the person next to you. Go. What is all that representing? G of t times dt. Tell the person next to you. Somebody new. Can you tell me what g of t times dt means? Yes, ma'am. Okay, right. So it's one little change in y. It's one little change in y for some value of the rate, right? So when wherever t is at, we get a rate, and then that rate times a little change in t will give us a change in accumulation or a change in y. Okay? So again, that's where we see constant rate of change right there. That whole expression is embodying constant rate of change. Okay? What else? So we got that. We know that the integral sign means what? Sum starting at
4.
a equals 4 up to x, right? And then x itself changes, right? X varies so that the right-hand side varies, and we get all amounts of accumulation for all values of x on the right. And that's what that function gives us. And when I say accumulation, it's net accumulation, right? Change in accumulation starting from a equals 4. Okay, let's look at this one down here. So for this one down here, first of all, is it a valid expression?
No.
Yes.
Yes.
Is it a valid expression?
Yeah.
Okay, so maybe let me ask this question. Is it a function?
No.
Okay, it's not a function, but it's a perfectly valid expression. And what does the expression mean? So what is the meaning of that right there? A times sine of e to the a. What is that? That's our rate of change function. So instead of using function notation, now it's putting the rule in there. So maybe, r sub b of a equals a sine. So maybe this is our exact rate function, r sub b. R sub b of a is a sine e to the a. So that's giving us exact rate. And so we could put r sub b of a in there, or we could put in the rule. And that's what they're doing here. So here they're just putting the rule in instead of putting in the function notation for the rule. Totally valid. So a sine e to the a is giving us exact rate of change. Exact rate of change for some accumulating quantity. So what we want to see is this 15 then, so our starting value is 10. And then we can think of this 15 as what? As a chosen value of x. It's like we had a function, and what did we do? We said, okay, we want to know what the value of the function is at 15. Do you see? It's like we had this function from 10 to x of a sine e to the a dA. And then what? We are just evaluating that function at a particular value. X equals 15. All right, so if that rate is r sub b of a, then what would using our notation that we've been using, what would we call this function? R? Capital A, right? Sub b of... Yeah, if it's the function, then it'd be x. But then if we're evaluating that function at x equals 15, then what we're really asking is, what is a sub b of 15? Sorry, you can't see that. So let's try again. I hit a button I didn't want to hit. I think we are back. All right. So we said if this is r sub b, say, then this would be capital A sub b, and specifically evaluated for a right side x value at 15. Does it make sense? Does that make sense? So we see this and say, oh, this came from some function that was started accumulating at x equals 10 up until x, and then we want to know then the amount of accumulation if x were 15. So that would be a sub b of 15 based on a sub b of x being 10 to x of a sine e to the a dA. Okay, so there's 4 more. Why don't you just take 2 or 3 minutes to kind of think through these other 4. So first of all, is it valid? Is it valid? If it's not valid, you can move on to another one. Okay? If it is valid, then you get identify all the parts. Identify all the parts. Introduce function notation where it makes sense. And describe the meaning as a whole. If you were lost on this, raise your hand and get help from one of us. If you got lost on what we were talking about there. Okay? Let's regroup. Here we go. So someone brought up a really good point on this one, and if you were confused, don't hesitate to speak up. Okay, don't hesitate to speak up. Did you see that we've got A's here, and then we have this value of we think of as A as 10 down here, and did you realize that those are two totally different uses of A, right? So down here, we think of little a as the x value, that's our starting value of accumulation. Okay? But now, what's a serving here? So this is it's just a dummy variable that's just serving as the x value that's going to change from 10 to 15. Okay? So hopefully that you thought of it that way. So this a here is different than what we think of as this a now. So this is the starting value, which we called a, but now this function, they're using a dummy variable of a to mean the x value that's going to change from a to x. So it's 2 different uses of a. Okay. Let's talk about let's go up here first. Valid or not? No, not valid. Because, for instance, if you wanted to do -3 to say 2, then what would it be? R sub h of 2. And all the way from -3 to 2, the rate would be this single rate. R sub h of 2 is a number. It's a single rate. And you would end up accumulating at that single rate from -3 to 2. Not at the changing rate R sub h, which is what we want. That's what happens. Okay, how about this one over here, this blue one over here? Valid?
Yes.
What is 2v minus natural log of v plus 1? Rate function, exact rate. What is that expression times dv? A little bit of accumulation. It's like m times a change in x. Constant rate of change, right? Constant rate of change. And then it's going to start at a. We're going to accumulate changes of that, right? Accumulate those changes starting at a, ending at x. So who came up with a name for this function that you're dying to share? How could I define this using function notation? Anybody? A sub w. Beautiful. Of x. Function of x, the right-hand side to where we're accumulating. Okay, this one here. Valid? Totally valid, right? And so cosine x plus x cubed is the rate function. Times dx gives us a little bit of accumulation. Essentially constant rate of change, right? Constant rate of change. And then we're going to start accumulating at a equals 0 up until final value of 8. So now we don't want to use x, right? So we want to use something else. Say a sub m of, right, so if we had the a sub m function, then what that would be doing would be evaluating that a sub m function at the particular value of 8. Good or not?
No.
Doesn't work. T's are the same. It doesn't do what we want it to do. Doesn't do what we want it to do. Any questions on this? Okay, so we've got this accumulation, net accumulation function, exact, and now we're starting to talk about evaluating it at a particular value of x. Okay, so when you do a sub m of 8, what do you get? Do you get an expression? Is it a function? Do you get a number? What do you get?
The total amount accumulated from 0 to 8.
And is that an expression or a number or what? What is it? It's a value, okay? It's a number. It's the amount of accumulation you get starting at 0, ending at 8, if you accumulate at this exact rate from 0 to 8. So this is a number, right? It's the value, it's a particular value of the function. A value, okay? How do we get that value? Do we plug 8 into cosine x plus x cubed? Do we plug 0 in? Right? So this notation is it's symbolic of a number, but it doesn't allow us to really compute it. I can go into does anybody remember what it was? So I can do 0 to 8 cosine x plus x cubed. All right, so there it is, 1,024.99. That would be our what? A sub m of 8, 1,024.99. It's how much accumulation, total accumulation you get, starting at 0, ending at 8, with a rate function of cosine x plus x cubed. Notice I needed GC to do that for me. There was nothing I could do to do that. So let's talk about that. Get my rights here. So we say, what's different about the exact net accumulation function, say a sub f x from a to x, versus the kinds of functions you're used to? Sine 3x, x squared minus 5x plus 4, square root of natural x minus 2 over e to the 10x. So what is different about this new function that we have, this integral function, versus the kinds that you've seen your whole math career? So we just said it, Jacob.
Our new function is summing up all the values.
Okay.
T.
Right.
The ones we're used to are just single values at a time. They're not really summing them up.
Okay, but, all right, maybe. But so this is what we were just talking about. So what's different? Yeah. Right. These are computable, right? So that we can readily generate values of the dependent variable just by taking the value of the independent and computing it based on the rule. Well, that rule doesn't lend itself for computing a value. I had to use GC to get that value. Do you see that? Okay, so this is the difference between an open versus a closed form expression. The rest of the semester, this is going to come up. So we're going to introduce it today. What kind of expression is this for this function? This is open form. So this new function, this net accumulation function, is an example of a function expressed in open form. Okay? What does open form do? It reflects a process, right? It took us a month to figure out all the meaning that's in there. There was a process from rate to accumulation that's reflected in that. Remember when you see that, you think of the A rule, okay? It does not involve a formula by which values can be computed. We need technology. If we have a value of the independent variable and we want to get amount of accumulation or net accumulation, we need technology. It's conceptual, okay? It's conceptual. As opposed to closed form, like a polynomial or a trig function or an exponential function. These readily generate values of the dependent variable. They're computable. So this is what you're used to your whole math career. Okay? And so as opposed to being more, the open form is more conceptual, closed form is more practical. More practical. memorize this. Learn. So yeah. So just memorize this because we're going to be using this terminology. And when we talk about open form versus closed form, you just have to know immediately what we're talking about. Okay. So you're going to memorize this. So to get net accumulation, we only have open form. We don't have a closed form version of this net accumulation, but this is going to be a major goal that we're going to embark on in the next month. Our major goal is we want a closed form. Of net accumulation. We want to be able to compute, generate lots of values of net accumulation given values of the independent variable quickly and easily. So this is our next journey now. So we've taken this journey from exact rate to exact accumulation, and we've got this function that we've built, but it's a little bit limiting because we need technology. We can't get those net accumulation functions in closed form yet. So that's the next journey we're going to start, is how can we now write this net accumulation function in a closed form? So we can spit out lots of values of net accumulation or total accumulation for various values of x, the independent variable. So that's our next endeavor. And the way that we do that is we're going to start on Monday by reversing this process. By talking about, we know how much of a quantity we have at every moment, and we want to know how fast it's changing, right? This is going to be the reverse. This is what allows us to then come back to our net accumulation and figure out how to get closed form accumulation functions. By embarking on the reverse process here in the next, but this is going to go a lot faster because of all the tools and building blocks we've done for finding net accumulation. Okay,
Oh my god, it's like
Okay. So the next we'll do a little unit here, and we're gonna talk about parametric functions and use GC to do parametric functions. So Tuesday, we're on track to be finished Tuesday with the big project. It's a major project. It's worth more than